Thanks for staying. I really appreciate that. In an ideal world, if I make a code change and then run my tests, a test immediately fails and tells me that I broke something if I made an error. In reality, however, that feedback cycle is often much longer. We work with teams where it takes hours, days, weeks, or sometimes months between introducing an error and a test failing that reports that there's an error. And this longer feedback cycle adds a lot of accidental complexity. Because if I break something now, immediately get feedback, it's very easy for me to pinpoint the root cause, because I can still remember what I did and there's nothing else that happened. If there's weeks or months between, I can't remember what I broke. And there's also so many other things that happened in between that it's a lot of effort to find what went wrong and to fix. Unfortunately, if once you have a lot of tests and a long-running test suite, it's often non-trivial to speed this up, maybe because there's other systems you need for the tests to run, or there's hardware involved, so often parallelization is not trivial. But the simple idea to still get very quick feedback is not to always execute all tests, but instead select a small subset of the tests that's much quicker, that we run more frequently, and then get much quicker feedback. But this only works well if the small amount of tests finds a large amount of bugs. And there's a lot of research on how to pick those tests with the goal of, in a small amount of time, finding a large amount of the bugs that the entire test suite finds. And today I want to talk about the different approaches, how well they work, and how easily they are applicable in practice. And so that you know where this experience comes from, some background on me. I still have two roles. I did my PhD in software quality analysis. This is how I looked when I started my PhD. And I co-founded a company that builds these analyses. And this is how I looked when I finished the PhD. And I've been told it mostly says there was always enough food during the PhD. But the main point I want to make is a different one. I still look at this topic from both perspectives. And as a researcher, I'm interested in, is it relevant to know? Or does the approach really work? So Antti said this morning that AI is much more widespread in use than last year. But as a researcher, I don't care if it's AI or not. I only care about, do we get good results? And as the founder, I'm interested in impact. It's not enough if it's an academically well-working solution. It needs to be applicable in practice, be able to work with the data that's there, and have impact in really saving us feedback time. Last slide on background, that some of the companies we work with, you will notice some of them use robot framework and are here. But if I take a step back, the challenge that if software grows, functionality grows, and so do our automated tests, feedback times get longer, and we need to select the tests we run on a frequent basis is independent of domain, programming language, or process type. So what do I mean when I say I want to select a subset of the tests? And why might this be a good idea, and what are the consequences? Imagine this is our test cases. I'm not an artist, so this is a very simple depiction. Every gray rectangle is supposed to be the system, and the green bit is the part that the test case covers. So imagine we run them, and some of them fail. And unfortunately, as you know, there's not a one-to-one relationship between bugs in the software system and failing test cases. So the orange bug here makes 2 test cases fail, the pink bug makes 4 test cases fail, and the yellow bug makes 1 test case fail. And if we select a small subset and execute those tests, in this case, we have 3 failing test cases and find 2 of the bugs, the orange bug and the pink bug. So if we only run a small subset, we won't be able to find all the failing test cases, but we don't need this to know that there's bugs in the software and maybe fix it before we do further more expensive testing. And second, obviously, if we only execute a subset, there's no guarantee that we can find all the errors that the entire test suite finds. So depending on the use case we have to keep in mind how we deal with maybe not finding all the errors. I want to talk about 2 specific use cases for test selection that I see a lot of teams apply in practice. And the first one is for a quality gate. And what I had to learn through customers is that a long-running test execution is a scarce resource in itself. We have customers where the entire automated test run takes a month, especially if there's a lot of hardware involved. And if you have a bad version of the software, where one bug makes 1,000 of the 10,000 test cases fail, this one bug ruins the entire test execution, because after seeing 100 test failures and always being from the same bug, nobody analyzes the remaining 900 test failures to see if there's additional bugs. So this one bug drowns out all the other bugs. And what teams that have these test runs usually do is have a quality gate to make sure that the software is good enough to be allowed for it to run on the expensive test run. And test selection can be used to optimize the acceptance test suite or smoke test suite to use to quality gate this expensive test run. And the second use case, I think, is more intuitive. If you run your test during continuous integration, if they passed yesterday and you made a small code change today, if you now rerun all the tests, many of them probably cannot find a new bug because their code they test is not even executed. So during continuous integration is another use case to do the test selection. And during continuous integration, now, how do we handle incompleteness? For the first one, for the quality gate, our main goal is to find out if the software is too broken for the complete test run. So it's not a problem if individual bugs slip through. For the second use case, during continuous integration, we need to every now and then still run the entire test run to make sure that no bugs slip through that the entire test run could find. So I want to first focus on the use case of a quality gate and then on continuous integration. For the use case as a quality gate, I don't know anything about what changed since the last test execution in the typical scenario. So why can we even optimize? The answer is because there's a lot of redundancy in test suites. In other terms, there's usually clusters of similar tests. And if you execute the first test of a cluster, there's a lot of potential of finding new bugs, but then all the other tests in that clusters only at a tiny bit of coverage until we hit the next cluster. I have an example to illustrate what I mean. This is an open source Java system called Pixelitor. It's much like a very simple version of Photoshop or MS Paint. And I use so-called tree maps to illustrate the redundancy in the test suite of Pixelitor. This is the source code of Pixelitor. Every rectangle is a component of the Java source code. This is its files in the Java case classes and its methods. And the bigger a rectangle, the bigger the corresponding method in lines of code. Now we can use the tree maps to look at test coverage. This is the test coverage of the automated and UI tests of Pixelitor. If a rectangle is gray, then that means the method was not executed during the test run. If it's green, it means it was executed. And code coverage can be automatically captured through so-called code coverage profilers that run in the background. In this case, they attach to the Java virtual machine and record which code gets executed during testing. You can run this for unit tests, for robot tests, for end-to-end tests, for manual tests. So this is something that runs in the background and we can do for all types of testing. But now back to redundancy in the test suite. Now imagine we run the test suite. In the order it's typically executed in the Pixelitor. This paint program has blurs. And since this is important functionality for the paint program, there's tests for the blurs. And now we start the test suite. The first test is called test Gaussian blur. And every single method that test case executes is depicted in green and everything else is gray. Now the second test in this suite is called test motion blur. And now every method it tests that was not tested previously is green, and all the methods that it tests that were tested previously by the Gaussian blur are blue. You see there's some green bits, but there's a lot of blue. The third test is called lens blur, and you see there's even more blue code. And if we take a step back and we ordered the newly called code in green next to the tree map, you see that there's a diminishing return. There's a saturation going on. And now if we switch from the Pixelita toy example to a real-world software project, this is an example from one of our customers. It's a medical system, and the test suite runs 48 hours. And on this axis, you see time. On this axis, you see the percentage of code coverage building up during the test execution. You see in these plateaus that there's clusters of very similar tests. And when we hit the first cluster, there's a lot of new code getting executed, a lot of potential for finding errors. And as soon as we stay in the cluster, there's very little additional coverage happening. Now, we can do a lot better if we change the sequence of testing. And there's a whole research area that tried very many different approaches, and the best we found is this. We always execute that test next, that per second of test execution covers the most untested changes, untested code. And this first selects create and modify selection, then change view settings, then second layer. It's not important what these tests do individually, but you notice it's not blur, 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 but very different functionality. And if we take the step back again, you see that in 4 test cases that take pretty much the same time, we covered a lot more code. And if we apply this strategy to this test suite, we come from this picture to this picture. And the trick is, if we only execute the first part, if we invest like 5 or 8%, then we cover a lot more of the system. In this case, 8% was somewhere here, less than 15% of the code base, and here we cover almost the entire code base. And coverage does not mean fault-finding capability. So we've done a lot of empirical research to see if this actually matches by looking at bugs from open source data and using mutation testing to artificially introduce bugs and see if those selected test suites find them. And we see that on average, in 6% of the time it takes to execute the entire test suite, we find 80% of the bugs that the test suite can find. And in 11%, we find 90% of the bugs. So this works really well, but it's so hard to get to run in practice because for these approaches, we need test case specific coverage. So we need to measure every single test case individually in isolation. Sometimes that's feasible. Sometimes it's difficult. For example, if there's different programming languages involved, because then it's much more complex to measure that. So what we've tried in the last years is how well can we use other approaches, especially AI, that do not need test case specific coverage. And the basic idea is to sort those tests by dissimilarity, to break up those clusters. And one way to do that is to order them across a vector space. By some metric, there's a lot of approaches, for example, by textual similarity, by cloning between test cases, and so on. And then randomly select one, or maybe select the fastest test case. And then next, select that test case that is the most different from that test case. And then the test case that's the most different from the previous two, and so on. And now that's where AI comes into play. Because from our research projects, the best approach we've found so far uses embeddings in large language models and distance between LLM embeddings to draw up the vector space and compute the distance between the test cases. And this is much easier to apply because we only need the textual content of the test cases and we don't need to measure them during execution. And from our experiments so far, it's almost as good as the approaches that require test case specific coverage. Now, how does it look like for continuous integration? The key difference is now we know what changed. This is a tree map of our own code. in orange and red, you see our modified and new code. And now I run a time-lapse video of our automated tests. You see all the methods that a test execute in one frame. There's 30 test executions per second, and the frames start in white and then fade to green to see where test coverage builds up. But the key point is all the orange and red stuff doesn't get covered. And that shouldn't be a surprise, because when we wrote those tests years ago, we didn't know the new features that would come up and didn't proactively write tests for features that we didn't know yet. But if a test does not execute modified code, it cannot find a new bug that was introduced by that modification. And in that case, we had roughly 5,000 test cases, and only 4 of them executed the modified code. Not 4,000, but only 4. So almost all the test executions in that run were useless because they could not find new bugs. So, and the key idea of test impact analysis is we throw out all the tests that cannot find new bugs, and then we do the same resorting we saw in the previous case. And there we see in 1% of the time it takes to execute the entire test suite. On average, we find 80% of the bugs, and in 2% of the time, we find 90% of the bugs. But again, this only works if we have test case-specific coverage information, which is great if you do, but in most cases we don't. So how well does that work without? And there's different machine learning or AI-based approaches that work on that. And the first one we've evaluated is called predictive test selection. The basic idea is you correlate change information with test result information. That means you grab from the version control system which files were changed since the last test execution, feed them into machine learning model, and then feed it also the information which tests pass and which fail. So it learns for every single test case which files were touched in the past to make that test case fail, hoping that it learns if we tweak something here, this test will likely fail, so we should execute it now. Now, how well does this work? In this box plot, you see the time it typically takes to the first failure. And this is retest all. This is without any AI. This is the test impact analysis using coverage-specific information. And the lower the box, the better. So this one works really well, but it's really expensive to get the data. So how good does AI, does machine learning work that only uses the change and failure information? Unfortunately, very poorly. So it's almost the same as always running all the tests. So what we did was we fed it more information, including information about similarity between identifiers in code and in test cases. That's called information retrieval. It's a similar technology like in search engines. And we had a machine learning model where we fed all that in, and it worked quite well. And then we used something called explainable AI to know of the many things we fed in, how big is the impact of the individual factors. And then we learned the impact of this is very high and the rest is very low. So information retrieval alone works pretty much as good as all the expensive test case specific coverage stuff we did before. So that's why for our solution, we got rid of AI again and only use this now. So to sum up, where I looked at 2 scenarios, we used this for a quality gate and for continuous integration. And I looked at approaches that use coverage information and approaches that work without coverage information and only use test content. And the more information we feed into the models, if we feed change information in, the results get better. And when we use coverage information, it's better than content, but only a tiny bit. So I think the coverage-free approaches that sometimes use AI, they are not better, but they are much easier applicable. So I think for most teams, they will probably be the better bet, the easier way to get this thing to run. Now, for the last 5 minutes, I want to look at the question of defect prediction. Because with the test selection approaches, we can only find bugs that we already have tests for. But the promise of defect prediction is to predict before we ship our software where defects in production will occur, independent of whether we have tests for them or not. And if this worked, we could be way more effective. And it sounds really promising because for a decade, there's been research, especially my Microsoft research and other big companies, that always got a best research award on the big computer science conferences. And they pretty much did the same paper every year. They correlated information like how complex were changes, what code was changed, who did the change, and so on, with the bug information that they had in their bug databases. And they always resulted in 80% of the bugs on 20% of the components. And that sounds great. So we built this for our own system. And the first thing you notice is, if I hear 80% of the bugs on 20% of the components, it feels like 80% of the bugs are in 20% of the code. But if you look here, our components are not the same size. If we only take the 10 left ones and order them by size, then the two biggest ones, the 20% biggest ones, have 85% of the code. So, but if we predict that 80% of the bugs are in 85% of the code, then it's not very useful. And actually, none of the old defect prediction papers contain anything about component sizes. And there's even a competition with a lot of open source defect data. And you can submit your defect predictor, and then every year a champion is handed a prize. And one guy handed in a defect predictor that only sorted components by size, and he won the competition. So that was basically a way of demonstrating that a lot of the defect prediction work uses machine learning in a very complicated way to sort by size. And that's not useful. So for us, we want to have defect prediction on the method level. If the predictor tells me these 6, 7, 8 methods are very defect prone, and some of them really do have defects, it's maybe a useful thing. And the second thing we do different from academia is, in the research, there's no difference between future bugs and past bugs to have a bigger data set. But as a practitioner, I only care about bugs in the future. The bugs we had in the past, our customers have already told us about. So what we did is we trained the machine learning model on an old release. And then we looked at, were there really any bugs in the 2 years after this release that we had to fix. And of the 1,000 most defect-prone methods, we looked at the 50 that had the highest defect risk score. And now, I did this for 2 of our releases. And as a developer, if a magical black box tells me, I guess there's a bug in this method, but I won't tell you anything else because my machine learning model is a black box, we need a really high score. We need a high precision. Like 9 out of 10 need to be really buggy. Otherwise, I don't think my developers will keep looking into this. And from the 100 methods we looked at, 0 had a bug. So this did not work at all for us. Now, it could be because the information is just not on the data. It could also be, to be frank, I learned that we are a pragmatic community. It could be because we are too stupid. And to our rescue, there's other research papers that have done the same thing, method-level defect prediction about future bugs, and they said that it doesn't work at all. It's like a random coin toss. Performance is extremely poor, or to put it more optimistically, it's an open research problem. So as a PhD student, it's easier to do something new here than in other areas because none of the approaches work. I've included that here because there's a lot of companies that claim that they can do that, and there's research that claims that, but I think that snake oil, I haven't seen anything that works. And that's not because machine learning is too bad or LLMs are too bad, but I think the information is just not in the data, and then the machine learning can't extract it from that as well. So let me summarize. If your tests take too long, don't always execute all of them. There's a lot of approaches that work well in finding that subset that finds the most tests quickly now. And I'm happy to discuss which one works in your specific context, either at the booth or over beers later. Pardon? This one? This one, yes, sure. I think I have 5 minutes left for questions. Thank you.
I was hoping for more than 0 in the end, but
yeah, so were we.
Yeah, wasted time. Any questions? There.
Nice.
Oh, okay. Now,
Hi. One question. How good or how bad does random ordering the tests compare to the more intelligent orderings?
That's a very good question, because random is much better than the default sequence. As you notice here, we usually execute tests in the way they are ordered in the file system or by alphabetical ordering, and that's a very poor one. So optimistically speaking, it leaves a lot of room for optimization, and randomization is actually much better than the default order, but depending on how you randomly pick, it might be better or worse. And it's not as good as the different approaches I've shown. And the research always compares against random order as well.
Thank you.
yes.
In the model where you were showing where was your own code and you had the changes in the orange and the red, you were talking about kind of this overview. This is, again, code itself. This is not tests, right?
This is code, yes.
Yes. So you talked about your test suite as it is. How does the concept of I put in new code, I have to put in new tests as well, how does that change this whole picture? Does it change anything, or does it, how does that affect things?
Also a good point. This is mostly used for regression test selection. So for the test suite, that's there for a long time to see if stuff that worked before is broken. But what I didn't say is in those approaches, you typically, whenever a test is changed, you select it. Whenever a test is new, you also select it. So that it always gets executed, because if a developer changes a test, it's probably a good idea to run it. Also, if there's a new test, it's probably a good idea to run it.
Thank you.
But we don't need machine learning to figure out that the test is new or modified. So I left that out.
Hi. Elmar, I'm sorry, I had to go to the toilet for a brief second, and it seems you explained something that I didn't hear before regarding the content-based prediction. Would that be also possible with Robot Framework with the keywords, that we say, okay, instead of select the test that has the most tests, the most steps covered, select the test that uses maybe the most second lowest level keywords. For example, we have keywords click button. That is too low. That doesn't make sense. But which button is clicked? So for example, click button with a specific selector is something new code, at least in the front end. Is that something that could be a very easy approach?
I think it would be one distance metric, that you could order them by how far are the new keywords from the old keywords. And my gut feeling would be that the LLM embeddings already capture that as well.
Okay.
Next question. Here's one.
Hello?
Yeah.
Yeah, so a lot of times you mentioned during a speech, didn't work at all. So what is the point where you should just give up? Like, no point of going forward, this is as good as it's get. Or do you just keep looking for new solutions until you find the grail? Or is it like approach acceptable, doesn't work? No,
that's an interesting question. I think it depends on your role. As a PhD student, you can't really give up. But that wasn't true. You can publish a negative result. It's just much harder. Because if you have a positive result, it's the result in itself stands. If it's a negative result, you must show that it was not you that was the problem. So you have to include much more process. These 4 approaches, they good to work in practice. We have customers that use, for every single one of the 4, we have customers that use them and are successful with that. What doesn't work at all is defect prediction, and we've given up on that because I don't think it works from a perspective that it's useful in practice. Maybe in academia for other things, but not as a practitioner.
Thank you.
More questions? Anything from that side? Here, this one.
So, do you think there is room to make a automated tool that will give you the set of tests for the quality gate you should run?
Yes, we built one, and that's our business model. So I didn't speak about that on stage, but I'm happy to wear the sales hat at the booth.
Is he working for you?
No,
Okay.
not so far.
Could be. Maybe a new employee. Are you hiring? Hey, thank you, Elmar. Elmar will also be in the speaker's corner. There's your hockey jersey. Thank you.